In part 4, we wrapped up storage. Now we're tackling the network that ties it all together. And GCP breaks every rule you learned on other clouds. On AWS or Azure, if you want servers in the US and Europe to talk privately, you're setting up separate VPCs, peering connections, transit gateways. A mess. On Google Cloud, a single VPC can span multiple regions. You can place subnets in Iowa and Frankfurt, and they belong to the same logical network. Traffic between them stays within Google's network infrastructure, avoiding the public internet and slashing the complexity of cross-region connectivity. That's not just a feature, it's the kind of architectural advantage that makes multi-region apps cheaper, simpler, and more secure. If you've been wrestling with VPC sprawl on other clouds, Google's approach is a career-accelerating relief. A virtual private cloud is your own private, isolated slice of Google's massive global network. Think of it like having a traditional data center network, routers, switches, firewalls, but without buying a single piece of hardware. You define the IP address ranges, carve out subnets, configure routing, and control exactly which traffic is allowed in or out with firewall rules. Just like a physical network, by default nothing gets in from the internet unless you explicitly open a door. With VPC-level controls, you can even lock down Google-managed services like cloud storage so they're only reachable from within your VPC, getting the same isolation you'd expect from a private data center without the hardware. Here's the secret sauce that flips traditional cloud networking on its head. On AWS and Azure, a VPC lives in one region. If you need resources in 3 continents, you're building 3 VPCs and then wiring them together. Google Cloud's VPC can be global. A single VPC spans multiple regions, so you don't need separate VPCs for each geography. This diagram shows one VPC containing subnets in USS Central, Iowa, Europe West, Belgium, and Asia East, Tokyo. Because they're in the same VPC, these subnets can communicate directly. Traffic often remains on Google's network, avoiding the public internet in many cases. That reduces latency and minimizes the need for complex peering setups. With VPC flow logs, you can monitor traffic across these global subnets, updated every 5 seconds, giving real-time visibility. For a career cloud engineer, being able to design a truly global network with one construct is a huge productivity multiplier. The VPC is global, a single virtual network spanning all regions. Within it, subnets are regional resources that cover all availability zones in that region. Each subnet gets its own IP CIDR range. For example, a subnet in US Central could be 10.01.24, giving 256 private addresses. When you launch a VM, you attach it to a subnet. The subnet's region determines the VM's location and internal IP. So while the VPC ties everything together, workloads are placed in regional subnets for isolation and proximity. When you create a VPC, you choose between auto mode and custom mode. Auto mode spawns a subnet in each region automatically with default IP ranges, a fast start but limited control. Custom mode hands you the roadmap. You decide which regions receive subnets and exactly what CIDR blocks they use. CIDR, the notation that defines an IP address range and its size, like 10.0/1.024. No wasted IP space, no surprises. For any serious workload, custom mode is the standard, while auto mode feels like training wheels for quick experiments. Let's lock in the core concept. True or false? A GCP VPC is a global resource that can span multiple regions, while subnets are regional. The answer is true. Your VPC exists at the global level, containing subnets that are each tied to one region. A VM in Tokyo and a VM in London can be in the same VPC, but each VM's subnet is definitely regional. That distinction is the foundation of every networking decision you'll make on GCP. When you create a VPC in GCP, you choose between automatic and custom subnet mode. Automatic mode creates a subnet in every region with fixed IP ranges. Quick for a lab, but a mess for production, wasting address space and control. Custom mode gives you a blank canvas. You define only the subnets you need, in the regions you need, with IP ranges you choose. This single setting, subnet creation mode, is the difference between a tidy, secure network and a sprawling, uncontrollable one. Choose custom. Let's walk through creating a VPC in the console. First, name your VPC, something descriptive like production VPC. Then, the critical decision, select custom subnet mode, not automatic. Next, add a subnet. Choose a region, name it, and specify an IP range like 10.0.1.024, giving you 256 addresses. Click Create and you've got a clean, custom network with no unwanted subnets. Firewall rules in GCP are built from a set of essential components. You define the direction, ingress or egress. You assign a priority. Lower numbers win, so a low priority rule takes effect before a higher priority rule. Then you choose an action, allow or deny. The target narrows down which VMs the rule applies to, all instances, or only those with a specific network tag or service account. The source or destination specifies where traffic comes from or goes to, using IP ranges, tags, or service accounts. And finally, you state the protocol and port. TCP port 443 for HTTPS, and so on. There's also an enforcement status toggle for more granular control, but these are the core knobs you'll use every day. Crucially, GCP firewall rules are stateful. If you allow inbound HTTP on port 80, the corresponding outbound responses are automatically allowed. You never need a separate egress rule for the return traffic. When you first set up a VPC, default firewall rules may allow broad access. The first security step is to remove rules that expose SSH or RDP to the entire internet. Instead, limit SSH access to trusted IP ranges, your office, your VPN, using firewall rules that target specific VMs via network tags. This simple practice immediately reduces your attack surface and aligns with the principle of least privilege. GCP firewall evaluation works on priority. Lower numbers win. If you have an allow rule at priority $1,000 and a deny rule at priority $500, the deny takes precedence because $500 is less than $1,000. The classic beginner trap is assuming a bigger number makes a rule more important. That's backwards. A priority of 2,000 is weaker than 1,000. Always structure your rules so the most restrictive deny rules have the lowest numbers and broad allow rules sit at higher numbers. Quick checkpoint. When you create a VPC, which subnet mode guarantees you full control over subnets and avoids automatic creation of subnets in every region? That's right. Custom subnet mode is the production-grade choice. It keeps your network clean and under your control. A firewall rule that opens a port to 0.0.0.00 is a gift to attackers. Instead, always restrict source IP ranges to the smallest set necessary. Your VPC's private IP space, your office VPN, or a specific trusted range. Use target tags to apply rules only to the VMs that need them, not the entire network. For example, a web server rule should target VMs with the tag web server and allow inbound only from your load balancer's IP. By default, GCP firewall rules are stateful, so outbound responses are automatically allowed. The number one mistake beginners make is leaving the source range blank or set to 0.0000. Don't be that person. Cloud load balancing acts like a smart traffic cop, spreading incoming requests across multiple VMs so no single server gets crushed. GCP offers several load balancer types for different traffic patterns: global HTTPS for web apps, internal TCP UDP for microservices, each optimized for a different OSI layer. The core idea is always the same. A highly available software-defined balancer sits in front of your instance group and automatically steers traffic away from unhealthy backends. A common mistake: pointing a load balancer at a single VM instead of a managed instance group. If that VM dies, your app goes down. Start by placing your backend VMs in a managed instance group. The balancer needs multiple targets to be effective. For the exact lineup and current features, check the official Google Cloud Load Balancing documentation. Choosing a load balancer involves more than just protocol. You need to consider scope, layer, and whether the original client IP is preserved. For global web applications, the external HTTPS load balancer handles SSL offloading and multi-region failover. For low-latency UDP, the external network load balancer preserves client IP and works as a pass-through. Consult current GCP documentation for the latest features, but this cheat sheet gives you a quick overview of the primary options. Global HTTPS. Load balancing uses Anycast, one single external IP address that routes traffic to the healthiest backend closest to the user. A visitor in Tokyo hits that same IP as someone in London, but Google's infrastructure automatically directs each request to the nearest region. No DNS geo-steering tricks, just one IP with global reach. Here's a trap that breaks app logging. If you choose a proxy load balancer, your backend logs may show Google's front-end IP instead of the actual user's IP, impacting geolocation, fraud detection, and audit trails. The network load balancer is a layer 4 pass-through that often preserves the original client IP because it forwards packets directly to your VMs without proxying. However, always verify the behavior in current GCP documentation, as some features may vary by region. High throughput and minimal overhead make it perfect for latency-sensitive UDP or TCP workloads where source IP matters. Let's check your understanding. How does a single IP address provide global load balancing with low latency? The answer is Anycast. Cloud DNS is a managed Anycast DNS service that delivers low-latency responses worldwide. You define a managed zone, add records, and Google's infrastructure handles scaling. Many providers support DNSSEC, domain name, system security extensions that cryptographically sign your records to prevent spoofing and cache poisoning. Verify current cloud DNS DNSSEC availability in the documentation. A common mistake: setting a TTL too high during a migration, causing stale records to linger for hours when you need instant cutover. Use a tool like Dig to quickly test your DNS resolution before you trust it in production. Here's what you need to know about cloud DNS. Typically, DNS records don't update themselves as VMs come and go, so you'll want to check current docs for any auto-registration features. But you don't need that magic when you use a load balancer. A load balancer gives you a single static IP that doesn't change, even as backends scale up or down. So you point your private DNS zone at that static IP, and internal services always resolve correctly. No scripting, no stale entries. Public zones expose records to the internet. Private zones keep them within your VPC. Combine private zones with a load balancer, and you get reliable, hands-off service discovery. Cloud VPN establishes an encrypted tunnel using IPsec, Internet Protocol Security, a suite of protocols that encrypt and authenticate IP packets over the public internet. It's quick, cheap, and works from anywhere. Cloud Interconnect provides a direct private physical connection into Google's network, bypassing the internet entirely. Think of VPN as an armored car on a public highway. Interconnect is your own private bullet train tunnel. The right choice depends on your bandwidth, latency, and compliance needs. Here's a costly trap. Picking Interconnect for a small dev environment can drain your budget, while picking VPN for a latency-sensitive app can hurt performance. Cloud VPN secures traffic over the internet within minutes, perfect for development, backups, or moderate throughput needs. Cloud Interconnect is the enterprise play. A private physical link from your colocation facility or service provider straight into Google's backbone. A common mistake is assuming interconnect is always necessary. For many workloads, VPN with Cloud Armor is sufficient and far friendlier to the wallet. Partner Interconnect often provides a wider range of bandwidth options and can be more accessible through service providers without needing to colocate in a Google facility. Check current GCP documentation for the latest available speeds. Dedicated Interconnect offers a direct physical connection with high, predictable throughput, ideal when you consistently need that capacity and can colocate. For many organizations, Partner Interconnect is a flexible entry point before moving to a dedicated pipe. Checkpoint. Which hybrid connectivity option is best for a low-budget dev environment that still needs encryption? 1. Cloud VPN. It's cost-effective, encrypted, but shares internet bandwidth and has higher latency than a dedicated interconnect. A quick and common confusion. Peering is not the same as hybrid connectivity. Cloud VPN and Interconnect are designed to extend your private on-premises network into your VPC. Peering, both direct and carrier, is typically about optimizing your path to Google's public services like YouTube or Google Workspace, not providing a private IP link into your VPC. Direct peering means you connect your routers to Google's at a point of presence, POP, and share routes. Carrier peering means you buy that connectivity through a telecom partner. So if someone asks how to connect their data center to their GCP VPC securely, don't say direct peering. That's usually not the right tool for the job. Imagine your e-commerce site getting hammered by a DDoS attack at 3 a.m. Without a web application firewall, that traffic reaches your backend and takes everything down. GCP provides a WAF that sits in front of your global HTTPS load balancer before a single malicious packet touches your VMs. It absorbs network-level DDoS attacks automatically, and its filtering rules can block SQL injection, cross-site scripting, and other common web risks, the kind of threats cataloged by OWASP, the Open Web Application Security Project. Check the current WAF documentation for the latest rule sets. They evolve to match real-world threat intelligence. A typical use case: an online retailer configures the WAF to allow traffic only from countries where they ship products, instantly slashing the attack surface. That's one policy change, no code changes. But don't mistake a WAF for a cure-all. You still need input validation inside your app code to catch what the WAF misses. Checkpoint. What service sits in front of your HTTPS load balancer to absorb DDoS attacks and filter OWASP threats? SON. That's Google Cloud Armor. It uses pre-built rules to stop SQL injection and XSS at the edge. No code changes needed. You have two VPCs in different GCP projects. Maybe one for your data analytics team and another for your web platform. And you need private IP connectivity between them. VPC network. Peering makes that happen without sending a single packet over the internet. Google's software-defined network connects them directly, so latency stays low and traffic stays private. Two critical rules that trip up beginners. First, peering is typically non-transitive. Verify current behavior in the official documentation. But if VPC-A is peered with VPC-B and VPC-B is peered with VPC-C, A usually can't talk to C through B. Second, you cannot have overlapping CIDR address ranges between peered VPCs. Plan your IP space carefully from day one. After you peer, run a quick ping or netcat test between instances in each VPC to confirm the path works before you deploy production services. This is the pattern that makes central IT teams sleep well at night. In a shared VPC architecture, a single host project owns the VPC networks, subnets, and firewall rules. The network admin defines everything once. Then, service projects, each owned by a separate dev or data team with their own billing, attach to those shared subnets. The dev teams deploy their compute engine instances into the shared VPC, inheriting all the centrally managed security controls, but they remain autonomous in their own projects. One firewall rule applies everywhere. One subnet range is governed by one admin. It's the cleanest way to enforce a zero-trust perimeter while still letting teams move fast. Most people new to VPCs set up a few firewall rules and think the network is locked down. Here's the uncomfortable truth. If an attacker gets credentials to a VM or exploits a web app vulnerability, a firewall rule that allows HTTP on port 80 won't stop them. The most dangerous assumption is that a permissive port is safe. If your app has an injection flaw, the attacker walks right in. Real defense is layered. Use an identity-aware proxy, so SSH access requires authenticated, role-based identities, with no open port 22 ever. Put a WAF in front of the load balancer to absorb DDoS, and filter common attacks before they reach a VM. Route traffic through an internal load balancer so backends aren't internet-facing. And ensure outbound internet goes through a managed NAT gateway, never via a public IP on the instance. Every one of these layers forces an attacker to find another crack. That's the zero-trust mindset. Build your VPC assuming the firewall rules will be bypassed, and then add the guardrails that mean it still doesn't matter. Let's build a secure, production-ready VPC step-by-step in the console. We create a custom mode VPC named Secure Lab VPC, add two subnets, Web Subnet for public-facing instances, App Subnet for internal services. Then we lock down traffic, a firewall rule that allows HTTP only from the internal load balancer subnet. Next, we launch a VM without any external IP. And finally, we configure outbound internet access using a cloud NAT gateway so that VM can still pull patches and talk to Google APIs, all without exposing it to inbound internet. This is the house that Zero Trust built. For the exact NAT setup in today's console, check the current Google Cloud documentation. The concept is the same, but the buttons might have moved. Last check. In the lab, what made it possible for a VM with no external IP to reach the internet for patches? Hint. It's a fully managed service that gives your private instances outbound-only internet access. The answer: CloudNet. It acts as a gateway, translating your VM's private addresses to a shared public IP for outbound traffic, while blocking all inbound connections. That's how zero-trust networks stay patched without ever being exposed. Here's the non-negotiable checklist with the exact GCP services and immediate steps. Run through it when you spin up a new VPC. Use Cloud IAP so SSH never listens on a public IP. Put CloudArmor in front of your load balancer to absorb Layer 7 attacks. Route backend traffic through an internal load balancer. Force all outbound internet through CloudNet. And turn on VPC flow logs and firewall rules logging so you can audit every connection. Skip any of these and you're leaving a door open. This is the floor, not the ceiling. This is the canonical 3-tier web app on Google Cloud. Traffic hits CloudArmor first, blocking OWASP attacks and DDoS, then flows through a global Anycast HTTPS load balancer. The web tier sits in a public subnet, but the app tier is buried in a private subnet, reachable only through an internal load balancer. The database has zero direct exposure. No single failure point, no open door. One last lap. Remember that GCP VPCs span the globe. You don't need a separate network per region. Always build with custom subnets so you own the address space. And never trust a single security layer. Combine Cloud IAP for admin access, CloudArmor for edge defense, and private backends with no public IPs. Next up, Part 6, Managed Databases. We'll dissect Cloud SQL, Cloud Spanner, and Bigtable, and show you which one your app actually needs. See you there.